Hello everyone and welcome back to an L582 modeling and control of electric machines and drives. Last time we started talking about the starting of three-phase induction motor. Okay, we started the lecture talking about the synchronous motor starting, and we said that when you're talking about synchronous motor starting, that means the method we need to carry out to force the rotor actually to start rotating from the beginning, and that's what I mean by starting this motor, because the synchronous motor is not self-starting. But talking about three-phase induction motor, it's a self-starting machine. Okay, so once you plug the stator into a three-phase voltage, the machine will start rotating on its own. So what I mean by starting three-phase induction motor, like we said last time, is reducing the very high starting current of the motor. Okay, and why do you need to reduce this starting current? Like we said last time, we have something related to the machine, which is reducing the copper losses associated with an increase in the current, because you know the copper losses in the stator is pretty much 3I1 square R1. So once you reduce the current in the machine, that means you're reducing the copper losses. Yeah, and something about the grid you're connecting to. Okay, it's just because if you reduce this current, you basically reducing the voltage dip that happens to other loads connected to the same bus. Like we said last time, this very high current that your motor draws at the starting is basically causing a very big voltage drop over all the cables that connect your motor to the external substation and your grid you're connected to. And that means that the bus you're connected to, its voltage will drop, and that it's not that good for any kind of a load connected to this, especially when you're talking about motors, like we said last time, because you know the torque of the motor is related directly to the voltage. So this reduction in the voltage will severely reduce the torque capability of the motor, and it may just burn down if it have a heavy load. But that actually doesn't happen because the motor has some sort of protection over it. So most of the cases, the other motors that are connected to the same bus will basically trip off by the under voltage protection mounted in them. Okay, and that's all something we don't all need. So by all means, we need to reduce this starting current, which is basically high. Why it's high, like we said last time, because if you go back to your equivalent circuit, that is R1 JX1, and that is JXM, and that is JX2 and R2 over S, and that is V1, the voltage applied, and that is I1, the stator current. Yeah, the whole point is at starting, the slip equals 1, and that means this value R2 over S is now very, very small, because it's basically now equals R2 as the slip equals 1. And the resistance, any kind of resistance inside the machine, should be very small, otherwise it's a bad design machines, because the increase in the resistance basically increases the copper losses again, and that's not good for the sake of the machine's efficiency. Yeah, so by any means, you know that R2 is by nature it's a very small number, and the thing that was just giving it a big value is by dividing it by the slip, which is naturally a very small value, but at the starting it's not a very small value, it's 1. That means R2 over S basically equals R2, which is a very small number. And that basically will make the total impedance of the machine very small. And you know that your current I1 equals V1 divided by the total impedance of the machine. So whatever this total impedance is very small, that means the current is very high. Okay, this guy is very small, so this current is very high. And that's why at starting, the motor just draws very high amount of current. So like we said last time, we're trying to reduce this as much as we can. And how we can do this it looks simple, okay? That is your equation here, okay? So you have the equation of the motor current equals, like we have it here. I'm gonna just have it much bigger here. That is V1 divided by Z total, yeah? So it should be easy. You want to reduce this one. You have two options. Option 1, reduce the voltage, V1, or option 2, increase Z total, okay? So you have two options, even to reduce the voltage applied to the machine or increase the machine internal impedance, okay? How you do this? It's different methods. We'll just go through the most important one of them. But here, the most basic idea is you want to reduce this current, just go to the equation. So even reducing the voltage or increasing the motor's impedance, okay? The whole point to keep in mind this, go back to your torque speed characteristics, which equals 3 V Thevenin squared divided by R Thevenin plus R2 over S, that's squared, plus X2 plus X Thevenin squared, that is multiplied by R2 divided by S omega S, yeah? And you know, for the starting, the slip equals 1, okay? The whole point is that you've seen here, this torque of the motor is directly related to V Thevenin, as everything here looks constant because the slip equals 1. Okay, all the parameters, the R2, R Thevenin, X2, X Thevenin, and omega S, which is synchronous speed, everything here is constant. So basically, the torque at starting directly related to V Thevenin squared, yeah? And V Thevenin is directly related to V1, so that means the starting torque directly related to V1 squared. That's very important to keep in mind. Because like we said here, our first method to go with all the time is reducing V1 to reduce this starting current, yeah? That is I1. I'm gonna call it I1 starting just to make you remember this all the time, yeah? So the whole point is we wanna try to reduce V1 or increase the total. So if you reduce V1, and that is the whole point we wanna go, so V1, if it is reduced, that means your starting current will reduce also, okay? And that is good thing, okay? But at the same point, using this equation, you know that if V1 reduced, that means your starting torque will also be reduced, okay? Because also a starting torque related to this, and this is absolutely bad. So reducing the voltage will solve you a problem, which is reducing the starting current, but it will give you another problem, which is reducing the starting torque, okay? But again, nothing comes without a cost. So that's the whole point to keep in mind, yeah? You can reduce the voltage, reduce your starting current, but making sure that actually comes with a cost that it will reduce your starting torque. So it has to be totally calculated to know if your motor will have enough torque at starting to withstand the load that needs to go up with it, okay? So that is an engineering problem to solve. But like I said, most of the time it's inevitable. We have nothing to do here, okay? All the time you have to pay something to get something, okay? But something to keep in mind, yep. So let's just try to investigate those starting methods, okay? The very first one, okay, is we call it full voltage starting, or sometimes it has another fancy name, which is direct online, abbreviated as DOL starting, okay? What is this method? Long story short, we don't use anything to reduce I starting. What? Yes, actually you can do this. You're not actually just forced to use starting method with any kind of a motor, okay? So if you're talking basically, so mostly used with small motors, okay? So if you have just a small motor that drives a small load in something, so actually even the starting current is much higher than its own steady state current, but after all, it's still not that much, okay? So you use this if your starting current of the motor is not that big actually, so actually you don't need to reduce it at all, okay? And it's actually, you can use it, and it is just, you can justify this scientifically. It's just because it's a small motor and its starting current, even it is high for its own steady state current, but it's not that high for our system, and it can handle it without trying to add external methods to reduce this starting current, because everything comes with a cost. Yeah, so that's basically how you can just do this. And I'm gonna just take this chance and make you look at actually how we can connect our motor directly to the supply, okay? So this thing here is you directly connecting your motor, that is three-phase induction motor, okay, induction motor, okay, and that is how you can connect it to the supply. So first of all, guys, here is your three-phase voltage directly from grid, okay? That is the full voltage of a grid coming just directly to the motor, okay, guys? We don't do anything to reduce the voltage or something. It is the full voltage coming from the grid, okay? And here is what you really gonna see in the motor on the actual field, and that's why I'm gonna just take you with me to investigate this, okay? So this circuit here, we call this the power circuit, okay? And there's another circuit down here, and we call this control circuit, okay? So the power circuit, you will find it just near the motor, while the control circuit, it doesn't need to be near the motor. Actually, it can be some way far in your control room, maybe. So you can actually have some sort of a control room, and you can start and stop the motor from way far. You don't need just to go at the motor side position itself and just push the button to make it start. And that's much more convenient, and really you need this in, especially when you're talking about large facilities, okay? What's under the power circuit? So this guy here, those 3 points, M1, M2, M3, is your contactor points, okay? Or, yeah, so that's what I'm saying here. What I mean by the contactor points, the contactor is basically some sort like a circuit breaker, which is basically a switch, okay? So the contactor is a switch that can be opened or closed remotely by applying voltage to its internal coil to act as magnet and close the points. Easy as that, guys. So you're talking about something inside this contactor, like here, just a coil like that. And this coil is basically, you can remotely give it DC voltage or like that. So you can use this switch in your control room and just switch it on, and this will give you electricity to this coil, which is basically act like a magnet, and it will close down the points of the contactor to close these points here. And once it's closed, you have current going inside the motor, okay? If you switch off this switch back, then you don't have any attraction force like this, and there is some sort of a spring that pushes back your points out. Okay, guys, take some time to try to look at this contactor online. It's very handy to look at. So the whole point is, yep, the contactor is basically a switch that's being controlled remotely Yeah, it has an internal coil. Once you get electricity to this coil, it acts like a magnet, and it just closes its contacting point here, like here, those 3 points, and give the current to the motor. If you just switch off the switch going to it, you basically don't have any force of attraction anymore, and there is an internal spring that will push up your points back to make it close. So you have just 3 points like this, up and down inside it, okay guys, and they're just connected together like that's not connected together electrically, but it's just mounted on the same thing. The whole point is once you have electricity to this guy, it'll act like a magnet here, which will just push down those guys, so those will be just connected together here like this, and you have current going inside, okay? Once you just open up this switch, you don't have any attraction force like this, and those 3 points here are just connected to springs that is hanging then up here, okay? Okay, and once there is no attraction force to keep them down, this spring will just pop them up, so you have them disconnected from the lower 3 points, okay guys? That is what we call a contactor. And we use this, like we said, because we can switch it on or off remotely. It's not like some sort of a circuit breaker in your home switch panel, so you need to just go there by your hand and switch it on or off. No, like that, you can keep the contactor near the motor like this, but you can switch it on or off remotely, okay guys? So that is the main thing, which is just switch it on or off. That's your contactor. And you have other 2 points here. First guys, here are the fuses, just right in here, and the fuses, this protects against short circuits faults, okay? So you use this as a protection against short circuits. So any short circuit here, this fuse will be blown up and it will just disconnect the current from going to the motor, okay? The other guy here is what we call an overload, and this protects against overloading, okay? What is the difference between this and this? The overload and the fuse. So the overload, actually, from its name, it just protects against overloading, which is a little bit increase in the current that goes for longer times, while the fuse is a very high amount of increase in the current that happens in a very small time, okay? And why we need both of them here? Just we can use the overload and you will sense any increase in the current anyway. You don't need a fuse. No, from a protection perspective, you need to discriminate this fault. You want to know if the problem is a short circuit and you need a fuse to pick it up so quickly, or it is an overloading, while you can leave it a little bit of time if it's just a temporary and it will go back. Okay guys? Okay. About the control circuit, that's the whole point. Is just that's what you have in your control room, and you can use this to just switch on or off the motor, okay? So you use this start button here, which is most of the time is of the type push button. We call it like that. A push button, guys, is just basically it has the 2 points that can close or open, and you have here to push down. And once you push this down here like that, you're just connecting those 2 points together, and now you have electricity going on, okay? Once you just release your hand from the button, okay, it has a spring that is just take it up again. So if you want it to keep connected, you have to keep pushing on it, okay? So it doesn't make sense, okay? So the whole point, we just have a little trick here. So once you just push this button down here, okay, and you have this connected, you have power going to this, which is the coil of contactor, okay? So the coil of your contactor now have current going on. Like we said here, those points will just, you have a magnetic force to attract, and this will come down here and the points will be connected, okay? And once those points are connected, that is those points here. So this guy controls those points up here at the motor power circuit, and you have current going inside the motor. The whole point is there is just in the contactor, there is not just those three main points that have the power going to the motor, but it has some we call auxiliary points. So it doesn't have just those main points of the contactor, but you may have other points here. We call it the auxiliary points that also close or open with the main points, but use those for control purposes, like this one here. So this guy is an auxiliary point of the contactor. Okay, so what happens once you push the button down, you have electricity going to the main coil of the conductor, and when you have electricity here, the contactor closes its all points including this point. So this point closes here. So even if you just lift your hand from the button and it goes up here, yeah, there will be another way here for the current to go from this side to this side through this contactor point. Okay, guys? Here's your stop button. So, like I said, normally it's closed like that to keep the current moving. Okay, so once you push this down here, you're opening the circuit. So once it's opened, you don't have any current going through the coils of the contactor, and that means it will open the three main points in the motor circuit here, and it will also open this point here, and everything is dead. You don't have any current moving, so the motor stops. Okay, that's why you turn on or turn off the motor, either the start button or the stop button. The only thing here is locked here. It's an originally closed point of the overload. It's a closed point of the overload. Okay, so once these 3 points of the overload, since that there is an increase in the current going to the motor, that means it's overloading for some time, because yeah, if it is just a temporarily and it will just go, that's fine. But if there is just a continuous increase in the current in the motor and just there for relatively long time, that will happen. Actually, it will open this point, open if there is overloading. Okay, so once this is opened, you don't have any current, so it just cuts the current going here, and that's will just close, or will open the points of the main contactor points, and it will just disconnect the motor from the supply. Okay, guys, so that's what actually you're gonna see in any kind of a motor. You have a contactor, which is the main switch that switched on or off the motor from the supply, and you have a fuse for overcurrent protection, for short circuit protection, and you have an overload for the overcurrent coming from overloading, and you have another control circuit which have a start button and a stop button to start or stop the motor, and it will have a point from the overload just to switch off the motor when it's just the overload which is connected to the motor, since there's an increase in the current that's there for a relatively long time. Okay, guys, so that's how you can connect the motor directly to the supply for the direct online method, and that here means you have the original starting current of the motor without any reduction. By the way, how can we calculate the starting current of the motor like this method? Okay, so in case of direct online like this, that means you're connecting the motor directly to the supply. How can you calculate the starting current of the motor? Okay, so how I can calculate the starting current of the motor? Okay, let me say, yeah, how to calculate the starting current of the motor. For this, you have two methods. The first one is using the equivalent circuit at slip equals 1. That easy. If you have the equivalent circuit, just place the slip equals 1 in this equivalent circuit and calculate for the current of the motor, and that's it. Okay. Use this if you have all the equivalent circuit parameters of the motor, which is not directly given in your motor catalog. Most of the time you need to do it in the lab to find your own equivalent circuit parameters, which is not in hand every time. So that's why the manufacturer has given us another thing, which is using the starting code given by the manufacturer of the motor. What is this starting code? That's code you can find it on the nameplate of the motor, okay? And this you can use it using a well-known table just to find out how much this current will draw, or how much this motor will draw current at the starting, okay? There is this table here. Let me grab it for you. Yeah. Okay. So yeah, this is this table here. You can use it. So there's that code letter. You'll find it, like we said, on the nameplate of the motor, on motors nameplate. Okay. So you'll find a letter from those A, B, C, D, E, F down to V. And everything has directly to find here. That is the starting kilovolt ampere bare rated horsepower. Okay, so you find those numbers. So for example, if you want to look at code G or something, it will be something between 5.6 to 6.3. That's coming by experience by the manufacturers. So code G means that you have 5.6 to 6.3 kilovolt ampere per each horsepower of the ratings of the motor. Okay, let us take an example just to try to calculate the current of the starting current of the motor. Okay, I'm gonna grab you here nice nameplate. Okay, that's a nameplate of a motor manufactured by Siemens. Okay, that's an actual nameplate of an actual motor. Okay guys, and that's a good opportunity just to look at this motor and just say how we can find the ratings. You can find normally on the problems we solve together, but for a real motor here. Okay, so there is different numbers for orders from the company, all that stuff. We just gonna try to find the most important things we need for our calculations. For example, that is HP, which is horsepower. So this motor rating is 30 horsepower. That is the output of the motor. The rated output power of the motor is 30 horsepower. Okay. Amps, which is the amperes. So that is the rated current, the rated ampere of the motor, not the starting current. You know, the starting current is different from the rated current. The rated current is the current that the motor draws when it has the rated load connected to it all the time. Okay. The RPM, revolution per minute, that is the rated speed of the motor. Okay guys. Duty, until a continuous duty, that means your motor is designed to work all the time without disconnections, because it's different for the design to design a motor that works all the time. It works sometime and disconnects. For example, your home blender you're using in your kitchen, your motor is designed not to be continuously working, but rather it just handled to be switched on and off frequently. Okay, so it's different. Okay guys, another thing here, that is the volts here. That is the volts, 460 volts. That is the rated line-to-line voltage of the motor. Hertz, which is 60 hertz, the frequency of the motor. Okay guys, another stuff here, see that is NEMA design code. Remember the design code of the motor, that is B design. So that is the NEMA design code. Okay, so that's which code of the motor, A, B, C, D. Remember the standardization page you have to look at online for doctrinizing the material. That is the NEMA design code B, which you use back in the testing of the motor to find out how to find X1 and X2. Go back to the testing lectures if you don't remember. Another thing here, that is what we need, kilovolt ampere code, which is G code. So that's the kilovolt ampere code of the motor, which is basically the starting code. So you have it like starting code or kilovolt ampere code. It is the same thing to look at. Okay guys, so that's code G. So if you have this particular motor, you know that's code G. So you go back to this and you know that's code G, and that's anything between 5.6 to 6.3. Okay guys, so if you want to calculate the current, the starting current for this motor, I'm gonna go this for code G. Okay, it is anything between 5.6 to 6.3. 5.6 to 6.3. I'm gonna pick 6.3 because that is the maximum, which is the worst case. Okay. Kilovolt ampere per horsepower. That is what's saying the table. Kilovolt ampere per horsepower. So the kilovolt ampere starting equals 6.3 multiplied by, or 6.3, which is kilovolt ampere, so 6.3 multiplied by 1000, because that's kilovolt amperes, per each horsepower, so you re-multiply it by how much horsepower you have for the motor, which is 30. Like here back, that is the horsepower, it is 30 horsepower, yeah? So you multiply 6.3 by 1000, because that's kilovolt ampere, by 30, just multiply by 30, which is the number of horsepower rated of this motor, okay? That is the kilovolt ampere starting, which is basically the V1 I1 multiplied by 3, because you know it is the total, so that 3 V1 I1, that's starting, equals 6.3 thousand multiplied by 30. Okay, you need to find V1, which is the voltage of the stator per phase. The voltage here is 460, so this V1 equals 460 divided by square root of 3, because that is by default is a Y connected. Okay, and the given in the nameplate is a line-to-line voltage, and you need to get it to the phase voltage here, which is you divide it by square root of 3, because that's a Y connected. So everything here is known. Now you can find I1 easily. Okay, guys? And like we've seen here, the motor is just Y connected, so the line current equals directly the phase current. So because that is a Y connection also, the I line to line at starting equals directly I1 at starting, which is the phase quantity. So you didn't need to convert it, because we mostly keen on this, the line current, not the phase current. So after you just find the phase current, you need to transform it to the line current. So it depends on the connection. If it is delta connected, you need to multiply by square root of 3, and for delta connection, the V line equals V phase. But because we have a Y connection here, the V phase equals V line divided by square root of 3, while I line directly equals the phase line. So you don't need to do any conversions here. Okay, guys? So that's how can you actually find the starting current of the motor without the need for the equivalent circuit, if you know, or if you have the nameplate data for this motor like we have in here, which is basically the starting code and the rated voltage. And yeah, you can just use this table to find out how much current actually the motor can draw at starting. Okay, guys? By the way, that's the maximum, because we go with the maximum value, which is 6.3. But you can also calculate it with 5.6, and that will give you the minimum expected value. And now you know your expected value for the starting current will lie between this and this. Okay, guys? Sounds good. So that was the first method, which is basically nothing. We didn't do anything to reduce the current, but we use this for small motors. That's why we can just consider it as a method. Okay. The second method here is adding external impedance to stator terminals. Okay. From its name, it's just you have your three-phase induction motor like this, and this is your three terminals of the motor. But before connecting directly to the supply, you can add here an external impedance for each of the three phases. We call it Z starting, impedance used for starting. Okay, and now we connect this to the supply. We connect this directly to the supply. Okay. Okay. What this impedance will do to your motor? The whole point is, here is your V supply, okay, and the voltage at the motor terminal here is V1, which is your voltage directly going to the motor, yes? And the current moving out here is basically the line-to-line current of the motor. Okay? So the whole point is, if you don't connect, or just before connecting this Z impedance, V1 of the motor was directly equals V supply, yes? It was just connected directly to the supply voltage. But after adding this impedance, V1, which is the motor voltage, will equal just V supply minus the current I line multiplied by Z stator. That's for each phase. Okay, guys? Basic idea is that this impedance will have a voltage drop over it here, which is just subtracted from this V supply before going to the motor voltage. And that's how we reduce the voltage. So the whole point is, with having this Z starting, you just added, you have this voltage IZ subtracted from V supply. So whatever you increase this Z, the total motor voltage will go down. And that's what we need, actually. Yep. So if you have the starting impedance goes up, that means the voltage drop over it will go up, and that means the voltage of the motor will go down, and that in turn reduces your starting current. Remember, because starting current equals V of the motor divided by the total impedance. Okay, guys? And that's how you can reduce the starting current. And yeah, if you know have all the equivalent circuit parameters of the motor, you can just use those equivalent circuits with this impedance. You just can calculate how much impedance you want to put here to just reduce the current to the amount you want to reduce it to. Okay, guys? So what are the pros and cons of this method? Okay, the pros, basically it is simple to implement. Okay, it's a very simple method. You just got an external impedance, basically a resistance and inductance, whatever you want to have, and just connect it in series. That's very simple to have. But there's a lot of cons here. Even it looks good, but yeah, that's not that good. What about cons you're having here? First of all, added components means more money to buy and to install and for maintenance. Okay, it's another component you're adding to your system, so it comes with a cost, it comes with an installation, you need to install it in some place, and that comes with maintenance cost and all this headache. Okay, guys, whatever any component you want to add to the system. The other thing is more resistance. Okay, because you're basically any impedance you have will have a resistive part and inductive part, or maybe it's all resistive, actually you don't have any inductance, and that's the most case we know. Okay, so more resistance means more copper losses, and that means less efficiency. Not efficiency of the motor itself, because you have an external thing, but the total efficiency of the total system will be reduced, because you'll have in total higher copper losses, because you have in this Z impedance out there. The Z impedance is basically a resistance and inductance, or even just resistance without inductance. So anyway, you will have a resistance, and this will have copper losses. Okay, guys? The other thing, less voltage means less starting torque. The problem we said before that, yeah, we reduce the voltage to reduce the starting current, but this will come with the cost of reducing the starting torque. But again, it's in the most of these methods inevitable. Okay, guys? Okay. That was the second method. Like we said, we now understand what's happening. Impedance added, that would have some voltage drop, which is in turn will reduce the voltage that's landing on the terminals of the motor, and reducing the voltage reduces the starting torque. That easy. Okay. Method number 3, going the same idea, is adding resistance to rotor winding via slip rings and brushes. Okay? Remember, we used this same method for controlling the speed of the motor. Remember we talked about speed control of the induction motor? We used this idea of adding resistance to the rotor winding. Okay? Simple now. What will happen is adding resistance to the rotor winding, that means you're increasing R2. And by increasing R2, you're increasing the total impedance of the machine, and this in turn will reduce your starting current. Because if you remember, the starting current again equals V1 over Z total. So you've increased R2, and this increased the total impedance, so this guy goes high, so this I starting goes down. Okay? Simple as that. But again, let's look at our pros and cons. So let's start with the pros. First one, again, it is simple to implement. You just have a resistance and make it connected directly to the motor terminals. Okay? The other thing, and that's a very big advantage for this method, is it's reducing the starting current while increasing starting torque. And keep that in mind, increasing starting torque. And actually that is the only method that increases the starting torque. Okay? How this happened, I can actually go with you for a little bit. Go back to our torque speed characteristic equation here. Okay? Remember, the torque of the motor equal 3 V Thevenin squared divided by R Thevenin plus R2 over S, that squared, plus X2 plus X Thevenin squared, so it's multiplied by R2 divided by S omega S. Yep. For starting, like we said, this slip equals 1, this slip equals 1. Yeah? What will happen if actually you increased this resistance here that we're talking about? Okay? Like you see in here, guys, this is R2 in the numerator here. So if this goes higher, this starting torque goes higher with this. And that's the whole thing to do here. Okay? What will happen here is like you see in that. That's the thing. So, yeah, adding more resistance to the rotor actually increases your starting torque. And that is the only method of all the starting methods that actually increases the starting torque. And that's why it is a very, very good method to go with, because that is will give you reduction in the current which we need, but it's not even, it will leave the starting torque not touched, but it will increase it even more, and that's much good. But it's not actually the method we use most of the time, because again it have cons. Okay, what are those cons here? The first one, and that's very important one, is can only be used with wound rotor type. Remember, the wound rotor type is the only type of this rotor of the induction machine that you can access the rotor circuit. You cannot use this with squirrel cage. Squirrel cage doesn't have terminals actually to add any resistance to, and you know that for now that the squirrel cage is the most widely used one. You will not find wound rotor that much compared to the squirrel cage. So yeah, it's good, but actually it cannot be used with the squirrel cage, which is the most dominant type of induction motor out there. Okay. Other thing is the same idea. It is added component, which means more money in terms of buying it, installing and maintaining, just the same like added resistance or impedance to the stator winding we said before. The third thing, the same idea, is added resistance means increase in the copper losses, and that's a reduction in the efficiency. The same idea like also with adding resistance to the stator winding. Okay, guys? So that's the whole thing here. Yeah, you can use it, and it have a very good advantage of reducing the starting current while increasing the starting torque, but it comes with a cost. It has reduction in efficiency, more added money, and the most bad thing here just can be used just with wound rotor type, which is not the dominant type. The most dominant type you can see all the time is the square cage type. So anything that comes with need to accessing the rotor is basically something we don't like to have. Okay, it's not like that, but you know, it can only be connected via slip rings and brushes, and you know from the beginning any brush set means increased maintenance. Like we said before, we don't like to use brushes, because brushes means a lot of maintenance that need to go out all the time, and that's why we actually prefer the square cage. So if you don't have a wound rotor type for a reason, most of the time we don't go with a wound rotor type just for the sake of control. So that's the whole point here. Yeah, you can just I want to use a wound rotor type of a motor because I need to access the rotor circuit to add resistance going there to reduce the starting current. It's not that wise actually, okay? Because like we said, having a wound rotor and brushes that need to connect your resistance via an external brushes, that means a lot of maintenance that need to happen all the time, because these brushes will deteriorate with time and will have arcing and all that stuff, and we do not prefer that. Okay, guys? If you have a wound rotor type from the beginning, then you can use this method, but you don't go with wound rotor just for the sake of adding resistance to the rotor winding for starting purposes. Okay, guys? Okay. Method number 4 is using auto transformer to reduce starting voltage. Okay, what it means, that's pretty easy. Auto transformer, like the one we have in the lab, if you've seen, is just we start the motor with reduced voltage to reduce the starting current and gradually increase the voltage to the rated value after starting period pass. Okay, by the way, that's the whole point of talking about this. Yeah, so for those two methods, adding external impedance to the stator terminal, if you just use this for the sake of starting, what will happen is this impedance will have a switch. Okay, because you don't need it to be there all the time. Yeah, so this guy here, you will have a switch just connected in parallel with it like this. You will have same one for each one. Okay, because we just need them at the starting. After the starting passes, you need the motor, the voltage to go up back again to the rated voltage. We don't need to keep it reduced all the time. We just need to reduce it at the starting period, and that's it. So after the starting period happens, you just close this switch, and now you have a short circuit parallel with the impedance, where the impedance is out, and you're directly connecting this to the voltage. Did the same thing that goes with the adding resistance to the rotor winding, if you just use it again for the sake of starting. Okay, guys? That's, I mean, yeah, I just forgot to tell that. So yeah, we don't use them just and keep them there all the time. We just use them at the starting period. And after this period pass, we just need them out. So like we said, we have a switch in parallel with them. So you just close this switch, and that means they are out, and you're connecting the motor directly to the supply voltage, which is the rated voltage of the motor we needed. Okay, that's why I'm saying here, with the auto transformer, we just start with a low voltage and gradually increase it until we hit the rated voltage. And that means you are just reducing the starting current at the beginning, and that's it. Okay, if you remember, that's the whole point of an auto transformer, that it has winding like that. So you have V supply over there, and you have a tap here that can slide up or down to get you high or low voltage connected to your motor. Okay guys, that is V motor. And that's the whole point of this. Again, everything comes with the pros and cons. What about the pros of this method? The first thing to have in mind is flexibility. What I mean by this? That means you can flexibly change the transformation ratio of the O2 transformer to adjust starting voltage to the value you need. It wasn't that before with adding resistances to the stator or to the rotor, because that resistor, just keep it there. Unless you have different resistive banks and you just use them with steps, okay? But that will give you so much headache and will be much more expensive. But again, it's not that flexible. But here you have so much big flexibility. That means you can just readjust this up and down to get the voltage you need, actually, to just set the starting current to the value you need. So it has so much flexibility here. But it has also so much cons to go with. The first one, it is expensive because it's a whole transformer. It's not just here resistance or something, it's a whole transformer. So it is expensive piece of equipment. Okay, and also needs maintenance and installation requirements. Okay, it's another machine added to the system, because you know the transformer is basically a machine. Okay, again, it has internal resistance, so you have added resistance, and this reduces overall efficiency. Okay, because this transformer is not ideal. It has internal resistance, and that means more copper losses and all that stuff. Okay, again, reducing voltage reduces starting torque. So it's not like adding resistance to the rotor winding or something while you don't touch the starting torque, but basically increase it. Here you're reducing the voltage, just like adding resistance to the stator winding, and that means it will reduce the starting torque. Again, that cost comes with mostly every method of starting except for adding resistance to the rotor winding. Okay, so yeah, it's something mostly inevitable, but it's still a problem to face. Okay, guys? Okay. There's another two methods, which is basically the most widely used method, which is the soft starter and the Y delta starter, and I'll keep those to the next time. But for today, I just hope you understand what I'm talking about. We need to reduce the starting current of the motor, and that comes by reducing its voltage or increasing the total impedance of the machine. And we just try to look at the first four methods, which is the most simplest one to go with, which is direct online method and adding resistance or impedance adding to the stator winding, or adding resistance to the rotor winding for wound rotor type, or using an auto transformer to reduce the voltage at starting of the motor. Okay, they are all keep having the same principle, which either you increasing the total impedance or reducing the voltage applied to the motor terminals. Next time we'll go with the most widely used two types of starting, which is soft starters or wide auto starters. Okay guys, thanks so much for joining me today, and I hope to see you all next time.